Okay, this is a busy diagram, and it's worth it to look at a few things in here, and it's not as bad as it looks. This is one channel, and again, your device will have dozens of channels depending on which chip you're using. But in a channel, they're all going to have a mode that we're going to specify, like what are you? Are you a PWM today? Are you an input capture today? Are you just a counter? So we're going to program a mode, and we're also in this finite state machine here, and the mode will have if it's an output, we are also going to have to give it some data. Like if you're a PWM, when's your rise time, when's your fall time? And so we write to an A register and a B register. Those are two data registers, data A and data B. And both of those are double buffered. And I'll get into that in a moment. But I write my value for the data out, rise and fall time, for example. Then I specify what counter do I want. And I'm going to have different choices. I can use an internal counter, or a local counter B or C, or a global counter bus A, which is just another EMEOS channel. These come from other EMEOS channels. But I select a counter, and then as that counter is counting, I have two comparators, A and B, and these comparators are going to keep looking at this counter value and does it match A or B yet. And when it does match, it will do whatever it was programmed to do in terms of the output. It'll make it go high or low. Well, for an input, if I've got it programmed, it will capture whatever counter I selected into A or B. So those are the main parts. We've got comparators, we've got data A and data B, we've got an internal counter that we can use, and we can use a counter from a different EMEOS that is shared from another EMEO. Here's my edge detect for rising, falling. I specify polarity. I have a programmable input filter too. So I can have an input filter clock, and that is going to delay recognizing a signal just to deglitch it, take out noise. So here's my mode. Now, double buffering. Let's say I want to run at 2 kilohertz for a while. Ooh, now I want to go at 4 kilohertz. So I have two choices. I can try and go from 2 kilohertz to 4 kilohertz right away by writing to the A or B register. Or I could wait till the end of the current 2 kilohertz period and then update to 4 kilohertz. So that's what the double buffer is for. I can choose how I want the new frequency to be updated. And if I update it at the end of the current cycle, then the A value will be stored, and the channel will keep running on the older A value and will not update to use the new data A value until the end of that cycle. So internally, that's what's going on. To you, all these blocks are just a black box, you know, for software. So we have these different counter buses. We use the word time base and counter interchangeably. And you can either use the internal counter or time base or another EMEOS channel, and they're shared. So we have 5 different combinations that can be used. And here they're described. Let's look at very briefly a few of the modes that can be programmed. And the EMEOS has the mode single action input capture, which returns a value to the counter bus on an edge match of the input signal. So in other words, I select a counter bus, and so that it's watching this counter go, oh, an edge occurred, what count do you have? It captures that count, and now I can read it. And all of these little diagrams here are in the book, and they're all the same, where they show an example of an input signal, in this case, or it could be an output signal. Nothing's happening, but then I've specified a rising edge, And here's the counter bus. It's counting up. And it counts up and counts up, and ooh, this edge occurs. So now the flag is set that could cause an interrupt, and the value of the counter is captured into the A register. And nothing else happens until the next edge is detected, and the same thing in subsequent edges. So I've got a counter here. There's only one action here. I'm looking for one edge, and so the flag sets. For a counter, though, I'm going to use a modulus counter, and it could be a up counter or an up-down counter. And so I want to count up, let's say, to 1,000. In this case, 1,000 hex. So I count up, and this is an up counter, so it goes down to 0. And the flag sets. So I could use this for like a millisecond counter if I wanted to. PIT's a little simpler, but I could use this as well. And I can change the count value and count right to it that after the current cycle completes, start using a new count value and count to that. Okay, PWM. The simple PWM always uses the internal counter and or requires an internal counter, excuse me, in that channel. And we're going to be using a counter, whether it be the internal counter or some other one. And as that counter reaches a value that is pre-programmed in the A register, I'll have my first output transition. And as it reaches a value that's in the second register, the B register, then it will go to the other transition. I'm sorry. This is the slide has a little error here. Let me fix that. Simple PWM, PWFM signal, pulse width and frequency modulation. Okay. A little on the fly. Okay. So here we're going to use pulse width and frequency modulation, and this does require to have a channel use its own internal counter. So I can vary the frequency and or pulse width. And this is the most popular use of an EMEOS, certainly for at least one tier 1 for engine control. They use it just for PWM, but with the frequency modulation, they set it at 2 kilohertz and they only vary the duty cycle. So here I'm going to program the B with a value of 1,000, the A with 200. So when I reach 200, the output transitions. I keep counting up to the B value, which is 1,000. The counter resets and starts counting again, and the output transitions when the counter resets. So this will keep going. So here's my individual pulse width and frequency modulation, and I can change the frequency or the pulse width at any time. And then update it. Typically I'd update it at the end of the current cycle. So the PWM will cause an internal, or can use an internal or modulus counter of some other EMEOS channel. And this is for like the example of running an engine where you're doing PWMs to spark plugs and fuel intake, etc., off of a common time base. So there is a time base. I just program the high and low edges, and when the second edge occurs, then a flag is set in the peripheral channel. And just a little footnote, again, the worst thing that can happen is you recognize a false input for an input time device. So we have a filter, and all it is, very simple digital filter, where once an input transition occurs, that input transition will not be recognized until it is held for so many clock cycles. So if the transition occurs and then 2 clocks later it disappears, you can filter that out. It's noise. But after it occurs and has maintained its value for a number of clocks that you can specify, then it's recognized. So we're really delaying recognizing it, but by then we've got high probability that it's good. So that's the programmable input filter, and we're just showing here that certain transitions are filtered out, and we basically count until it's been active for a certain period. Let's go to the example in the book for the EMEOS, which is the modulus counter OPWM functions. In the version you have, well, you can look it up, the page there. And this will do a PWM to 2 different channels. I'd like you to take a look at the application note, the block diagram, what's going on, the steps, download it, and as you run the code, it will light up 2 LEDs, but it lights them up at a 1 kilohertz rate. So unless your eyes are really good, you won't see that they're flickering. But you can hit stop and see one on or both, hit go again and stop. You can see that it's changing. So I'd like everyone to compile it, download it, and run it, and I'll come around and see if there's any questions.